Let's start with the mathematical engine driving quantum computing, the exponential continuum. In standard theory, adding just one physical qubit to a register mathematically doubles the state space, creating a vast, frictionless landscape of computational possibilities. The formal equations dictate that an n-qubit register occupies a continuous tensor product space. To describe a normalized pure state in the system, you need 2 to the power of n plus 1 minus 2 real degrees of freedom. As n grows, that number explodes along a massive exponential curve. This formal structure traces back to the foundational axioms established by physicists like John von Neumann in the 1930s. In ordinary, low-dimensional laboratory regimes, this continuous Hilbert-space map works perfectly. It has survived every standard experimental test. Because of that perfect track record, the prevailing consensus in quantum hardware engineering treats scaling entirely as an engineering hurdle. The assumption is that reaching this massive state space is strictly a matter of suppressing decoherence, tuning gate fidelities, and shielding the system from local thermal noise. The industry relies on fault-tolerant error correction as the definitive bridge. The logic is straightforward. If you string together enough noisy physical qubits and extract error syndromes efficiently, you can build perfectly protected logical qubits capable of traversing this entire mathematical continuum. But a theory can use a continuum successfully without that continuum being physically available at an arbitrary infinite resolution. A smooth, fluid field maps perfectly at the macroscopic scale, but fails completely below molecular granularity. A large quantum computer forces us to ask whether the exponential Hilbert-space continuum is physically instantiated or merely a successful formal extrapolation. To approach this, we have to enforce a strict boundary between the mathematical equations we use and the physical reality they attempt to describe. In a framework known as TCGS-SEQUENTION, this is the distinction between the map and the territory. The territory is a four-dimensional, non-temporal counter space. What we observe in our three-dimensional world is simply a projected shadow of that counter space. Hilbert space is an exceptionally powerful operational calculus used by observers trapped inside that shadow. It organizes amplitudes, phases, and entanglement data with incredible precision. But it is entirely a map. It is not the territory itself. Assuming the map's exponential continuity extends infinitely downward is a category error. Just like classical mechanics, a map can be highly accurate in one regime and hit a structural wall in another. Circuit, the sequence of logic gates, the duration of coherence, the operational time, are purely shadow-bound parameters. They are indices guiding our reading of the map, not literal evolutionary dimensions of the underlying territory. When we build a large-scale quantum machine, we are not computing inside the territory. We are probing the limits of our own map. We are forcing the shadow to physically instantiate exponentially many continuous degrees of freedom simultaneously. If that physical projection bandwidth is finite, then the difficulties engineers face in scaling quantum computers are not hardware bugs. They are the initial friction of a foundational failure, where the map reaches a resolution it can no longer support. Physicist Tim Palmer formulates this boundary mathematically through rational quantum mechanics, or RaQM. RaQM acts as a precise, finite admissibility challenge to the standard Hilbert-space continuum. Palmer does not modify the Schrödinger equation. Instead, RaQM targets the geometry of the state space itself. It restricts the specific mathematical bases in which a quantum state can even be defined. He applies strict, rational constraints. The squared amplitudes and phase ratios are restricted to rational numbers, defined by a granularity parameter called L. The continuous Bloch sphere fractures into a discretized Riemann sphere. The coordinates are no longer an infinite smear, they snap to a finite geometric grid. By enforcing these arithmetic rules, RaQM produces the impossible triangle corollary. It proves mathematically that many unperformed counterfactual bases, alternatives standard theory assumes are perfectly valid, are structurally inadmissible. You cannot ask the system to calculate them. The standard quantum mechanics is recovered only at the singular limit where L equals infinity. It is a mathematical idealization, not a physical mandate. By stripping away the infinite continuum and replacing it with rational constraints, RaQM demonstrates that we can maintain quantum mechanics' predictive power while explicitly denying that infinite mathematical continuity physically exists. Standard quantum theory relies entirely on complex numbers and imaginary phases. This raises an immediate mathematical problem. How can a finite, discretized system replicate that grammar? The supplementary material for RaQM answers this by reconstructing the imaginary unit, I. Instead of treating it as a foundational continuum object, Palmer defines it as a literal permutation and negation operation, acting on finite 2-bit strings. Scale the granularity to L equals 4, and this simple mechanism expands. 4-bit strings generate complex quaternionic structures. These are the exact algebraic relations needed to govern rotations and spin kinematics in quantum mechanics. Grounding this in finite geometry shifts our interpretation of measurement. We move from treating Born's rule as chance towards seeing it as discrete proportions. Under this model, Born's rule is no longer an expression of inherent source-level randomness. The probabilities emerge as projection partition frequencies. They are the physical proportions of +1 and -1 entries derived directly from the bit strings. Complex phases, quaternions, and probability weighting, the essential quantum toolkit, do not require a continuous-based reality. They can be perfectly simulated by finite shadow grammar. This sets up an inevitable collision. The linear growth of a system's finite descriptive capacity runs directly against the exponential demand of continuum quantum mechanics. This chart shows exactly how that collision plays out. On one axis, we have the linear growth of a finite quantum information capacity, bounded by L. On the other curve, we have the continuous degrees of freedom demanded by the standard formal theory. The admissibility pressure builds until the exponential algorithm asks the shadow to realize degrees of freedom it simply cannot project. That exact point of divergence defines a hard threshold, known as Nmax. This is categorically different from ordinary environmental decoherence. Decoherence is the suppression of interference due to an uncontrolled environment. Nmax is a state space availability failure. The map simply runs out of coordinate space. Shor's algorithm serves as a specific stress test because its advantage depends on coherent phase relations across a highly distributed state space. It requires maintaining a global interference pattern across the entire register, which directly strains the assumption that all Hilbert-space degrees of freedom are physically available. If Nmax is a true physical limit, it won't matter how perfectly engineers isolate the hardware. The exponential algorithmic advantage will structurally saturate. Finding empirical proof of this Nmax threshold requires precision. We have to separate ordinary hardware failures from genuine structured scaling deviations. We must account for artifact candidates. Calibration drift, leakage, thermal noise, these are local, protocol-dependent engineering limits. These are exactly the problems that fault-tolerant error correction is designed to fix. What we are looking for are invariant candidates. These are algorithmic scaling deviations that persist across entirely different hardware architectures. They correlate strictly with the distributed Hilbert-space demand, not local noise sources. This matrix charts the projection bandwidth taxonomy. It maps quantum protocols not merely by their raw physical qubit count, but by their effective demand on the admissible shadow resolution. In the lower left quadrant, we have low entanglement systems, stabilizer states, and single qubit rotations. These may involve large numbers of particles, but their physically relevant states are structurally constrained. Their success in the lab does not disprove Nmax because they never approach the projection boundary. But on the extreme high-demand end of the matrix, we plot protocols requiring sustained, globally structured state-space relations, like Shor-type phase extraction. As these scale, they collide directly with the theoretical projection bandwidth limit. A structured signature of Nmax would appear as a mismatch, where increasing error correction improves local noise, but fails to restore global algorithmic advantage. If this deviation persists across diverse platforms and specifically tracks with distributed state space demand, it points to a physical boundary in the map. This brings us back to the rule of non-reification. The predictive success of a mathematical map does not mean it is the territory, and conversely, finding finite admissibility does not mean the underlying universe is literally a digital bitstring machine. The TCGS-SEQUENTION framework uses Palmer's finite model as a necessary disciplinary tool. It prevents physicists from idolizing the Hilbert-space continuum, treating it as an ontological reality rather than a highly effective calculation grid. Future scaling experiments must prioritize mapping this boundary. Instead of jumping straight to RSA-level factorization, researchers need to deploy intermediate tests, nested interferometry, and algorithms with tunable state space spread to carefully isolate exactly where the coordinates fail. We can view quantum computers as cartographic instruments. Their purpose is to find the precise edge where our continuous map finally breaks down. The shadow may compute, but it cannot exceed its projection bandwidth. Hilbert space is not the territory, it is the map, and quantum computing is about to show us exactly where that map ends.